Hello, everyone, and welcome to Intro to Functional Programming. So, by the end of this lesson, I hope that you will be able to explain at least 3 general tenets of functional programming. So this is a pretty sharp contrast with the object-oriented stuff that we were talking about yesterday. I can't think of any problems that you can solve with OOP that you can't solve with FP, or the other way around. These are ways of thinking about how we structure our solutions to things. Doesn't open up necessarily any like wildly different possibilities or anything, but they're two wildly different mental models for how programming should work. Cool. So just like we've done the last couple days, I want to, hello, Katie. We're going to start off with some reading. So I'm going to give you the Functional Programming Wiki article. Just like yesterday, like you're not going to understand all the words. Totally cool. Like soak what you can out of it, and then we'll start talking about it. Hey, Jack. So there's the link that we're reading. Let's start with 6 minutes. Go. Let's keep going. Another minute. Let's get back together. So give me some immediate impressions, especially contrasting this with the stuff we talked about yesterday.
It seems more mathy.
Way more mathy, more academic in general. Lots of research. I don't think anybody researched OOP. Yeah, there's like math departments that work on this. Other impressions?
It's more strict.
Yeah, way fussier about just about everything. Other impressions?
Has benefits.
Yeah. So like being fussy and strict about this kind of stuff, why would they do such a thing?
Eliminate bugs.
Alan, go for it.
Eliminate bugs.
Eliminate bugs by doing things like, especially state. If we don't worry about state is the cause of 90% of our bugs. So if we don't have it, that's 90% of our bugs gone. If our programs are all deterministic, meaning that if given the same inputs, always produces the same outputs, then at that point, your program becomes kind of like a mathematical proof. That's a hell of a lot better than hope there isn't an illegal state hiding somewhere in this program.
Did OOP come from anything? Because it says it came from the lambda calculus.
The lambda calculus. Yes, it did. And it's mentioned briefly in there. But plug in my whiteboard. So there's the lambda calculus. Sometimes you'll see that written like that. And then there's the von Neumann. Fuck, there's a third word in there. It's the von Neumann style. That's what the programming style is called. But there's a math version of it. The von Neumann. Von Neumann style, let's call it. So the difference there is that von Neumann style is about state, and more state. So from that, we got procedural programming, and then from that, OOP. I'm trying to think if there's an exception to this, and I kind of don't think there is. Von Neumann style, you could call interchangeable with imperative. So imperative is, I'm giving the computer these instructions. Store this thing in this memory address, then perform this calculation on it, then do this, then do this, then do this. Imperative, telling it what to do. That's literally what procedural programming is. Object-oriented programming has a little bit more structure around it and has these concepts of like nouns and the verbs that they can take on each other. It's still fundamentally kind of the same thing. We contrast that with lambda calculus leads way to declarative programming. Declarative being contrasted with imperative. Declarative is, this is the thing that I want. I don't care how it gets done. 1 + 1, imperative. Sum 1, 1, declarative. Two very different styles. And in fact, functional programming, this is also in that article tucked away in one of the historical anecdotes. In the 70s, there's a famous lecture given called Can Programming Be Liberated from the von Neumann Style? But since the von Neumann style was state, 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 variables, side effects, mutations, state, 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 state. And I mentioned that state means bugs. State's just so fucking hard to reason about. So, as this lambda calculus thing from the 20s and 30s was turning into functional programming in the 70s, this was like a call to arms against imperative programming and saying like, we could do better. In practice, these like declarative and imperative styles, functionals like has been really hot for a while. I think people are starting to get tired of it. So I think OO is kind of coming back in fashion again. It'll keep happening. Literate. Mathematical. Because at some point, if you run too far in either direction, they start becoming almost parodies of themselves. The functional programming solutions and things, when taken to their extreme, become almost impossible to read and reason about. And that was the whole fucking point, is that that was supposed to be like a more pure way to talk about it. Really, OOP runs into the same problem. Here, I'll show you Enterprise FizzBuzz. It's a classic. This was somebody making fun of object-oriented programming. So if you've never seen FizzBuzz before, anybody know the rules for FizzBuzz?
Yeah, it's like every if it's divisible by 3, it's got to be fizz. If it's divisible by 5, it's buzz, and if it's divisible by both of them, it's fizz buzz.
Cool. And otherwise, you print the number. So right. It's like a dummy programming test. People will do this in interviews and stuff to just make sure you didn't lie. It's not supposed to be hard. So a solution to it looks like that. That one looks like Python. There's JavaScript. That's it. That's FizzBuzz. So if somebody FizzBuzzes you, they're like, cool, then this shouldn't be that hard. This should take you a couple minutes. And if you give people FizzBuzz questions, you got to be prepared for like half of them to be like, you got me. There's just a lot of money in programming. And I thought I might be able to like sneak my way in and learn on the job. Shit happens, seriously. So,
Wait, how does this tell if you're telling the truth or lying?
Because you go like, oh yeah, I'm a programmer. I built this. I built this. I built this. This is like as straightforward, like basic programming challenge as there is. And so if they can't do this, maybe they didn't do all that other stuff they talked about.
Okay.
Yeah, people just be making shit up. that is real. So somebody wanted to make fun of OOP, so they made Enterprise FizzBuzz. Oops. So here's all the files. This is what a pure OOP implementation of FizzBuzz would look like. So there's the factories. Let's see, the strategies. There's like hundreds of files in this. The is evenly divisible strategy. What else they have? So good. So at either extreme, like these tend to not look so great. And as trends, they sort of come in and out of fashion. FP is very hot right now. I wouldn't be surprised if it wasn't so much in 3 or 4 years. Let's see. One thing I want to call your attention to in particular, I think this does a good job of illustrating the difference between procedural and functional programming, and really just in general imperative versus declarative programming. It was in that Wikipedia article. I wanted to make sure you didn't miss it. This right here. Let's take a second and just like soak in these two approaches to this for a sec. Imperative style, declarative style.
For me, imperative seems like easier to understand at first.
Absolutely. Yeah. Oh, like, and every programmer would say that. So here's my gripes with it. Here, well, let's throw them in a text editor. In there. Okay, so this one looks, it starts like a lot easier to read and figure out. You can go step by step through it and figure out what it's doing, what the state of the application is at every step of it. There's this one, syntax, chains. Ugh. So a functional programmer probably wouldn't actually write it like this. You would take these inline Lambda functions and extract them out. So this one is saying, if we rewrote that one as like function is even, takes in a number, and then returns whether the number modulo 2 is 0. And so now I can replace this inline function with that. Same thing with the map. So the map is multiplied by 10. And it takes in a number and returns number times 10. So let's swap that out, multiply by 10. And then this one is sum. and that takes in a total and a number and returns total plus number. And so we can say that this is sum. Okay, now look at the difference between these two.
Now I like number 2.
Yeah, now this looks like a little story. That's not the end of the benefits to this, though. I can test each one of these individually. I can test them thoroughly as fuck. I can make sure that is even works with every single number representable by JavaScript, even like the ends of the boundaries. I can see exactly when and where multiplying by 10 will create like a number overflow. I can see, like I can write such thorough tests for all 3 of those functions. My wife just said, I can ride my bike with no handlebars. Well done. So this, I can't tear that apart. There's no, like, this can't reduce down any further than it already is. That's troublesome. Here's another thing. Here's the real reason that I am not so crazy about imperative programming. Places where errors can hide in this, like stupid stuff, like getting the greater than, less than turnaround, that kind of thing. Really not much of anywhere in here. That wouldn't like also just be a syntax error. Also with these functions, also not a whole lot of space for like a weird bug to hide. Let's compare that with this. So you could have gotten the scoping wrong for that variable. You could have left this off, and at that point you might be referring to a global I instead of a local I. You could have initialized it to the wrong number. You could have done less than when you meant to do less than or equal to, or greater than or equal to. This I needs to be the same variable as this. Your num list needs to be the right variable, so you're not doing result.length or I.length or something like that. You need to look up the right property on it. You need to increment it in the correct direction. You need to increment the correct thing, because if you have nested loops and you're doing I and J and K, you need to make sure you're doing the right one. Real easy to fuck it up. And it's also very common to sometimes decrement. So you got to make sure you're using the right one of those. All right, well, we have an if statement. Those of you who did the DOM calculator refactoring know how much I love if statements, because now we have a branch in the logic. For every single step in this loop, it either matches the if or it doesn't match the if. And since it's in a loop, our cyclomatic complexity on this is off the fucking charts. It grows exponentially with how big the list gets. And then in this, I need to look up the right index. Is it I? Is it I plus 1? Is it I minus 1? I have to modulo by the right thing. I need to make sure that I'm comparing it to the right value. Is this plus equals? Should I be doing some kind of incrementer instead? Am I looking up the right index on numList here? Should it be the same thing as it is here? If it's nested loops? You see where I'm going with this? Like, there is 100 places in 5 lines of code for you to make a mistake. So if you have thousands, tens of thousands, hundreds of thousands, millions of lines of procedural code, what do you think the chances are you didn't make a single mistake in those? Woof.
And the second example, is this also displaying the concept of, is it called higher order functions?
Correct. This filter takes in a function, and that's a function. It's also a first class function because I can pass it into a function just like I could any other variable. And in fact, this isn't actually the like FP way to write this. The way you do it is as a fat arrow. That's the functional way to do it. Exact same thing though.
The only difference is that you're writing it in ES6.
ES 2015. And yes, I'm using that fat arrow. And for functional programming kind of stuff, the only difference between a declared function like this and a fat arrow function like this, a function expression, is that this hoists. You can use a function before you actually have like written the definition for it. So even though this is here and the definition of it is here, that's not a problem. That's all hoisting is. Function expressions don't hoist. So you need to define it before you use it.
When you're writing your function like definitions like that, what is the best way to organize when you're declaring it above when it's actually being used?
So I actually really like hoisted functions because the order doesn't fucking matter. There are a lot of people that really don't like hoisted functions because most languages don't have them, and ergo that makes it confusing. So actually my preferred way to do it would not even be like this. My preferred way would be to have something like a module where I maybe take all of these things and I do something like module dot, so export is even, yeah, that looks right. Export const is even, nope. We'll look at the named export syntax, named export JS. Okay, you do the const. So you do something like this and then import it in from that module. So you do something like import is even from math. And then like you could do that for all of these, like multiply by 10 and sum. I think that's the more elegant way to do it.
And so you separated all of your math functions into a separate, what you called it, a module in math.
Correct. So yeah, like all these would just go over here. Like that. And you pull them in there.
I imagine when we start building out, more applications, the amount of modules will grow exponentially.
Yep, and modules are going to be a major theme of Mod 4 for us because we use them all over the place in React. All right, I want to talk about composition. So we talked about composition with OOP. Composition is even more at the core of FP. So as an example, this multiply by 10. That's not super flexible because what if I needed to multiply by 9 or 11 or 432? Like I need separate functions for all of those. That doesn't make a lot of sense. So you could have multiply by, and then like you pass in an argument, but we want to like limit the number of arguments we're passing in, and we want to try to make more things functions. So here's how we can make multiply by kind of simulate that sort of thing. So we make a function called multiply by, and it takes in a factor. All right, you ready to have your mind exploded? This is one of those things. What we're going to return out of this function is another function that takes in the number we want to multiply by. So it returns some function, we don't even have to name it, it's not important to, that takes in a number and returns number times factor. Here's how that gets used. All right, we want multiply by 10. Multiply by 10 is multiply by 10. It's the exact same thing we had before. Look at this for a while. You need to let this one sit in. This is heavy. We made a new function out of other functions. That's composition.
Does the so is it implied that number is always going to be 1 here if you're multiplying that by the factor that you're passing through?
No, this is what we're doing with like each of these. So we're doing multiply by 10. You're doing each one of these. We're applying that function. That applicative programming. We're applying that multiply by 10 function to each of these numbers. So that ends up being here. When we invoke multiply by and pass in a number, what we get back is a new function that takes in a number, but can see that factor. It's like it saves it. It's a new function that can remember this factor up here. That process is called closure. This inner function closes over the factor. So even though we executed multiply by is done. It's all over. We've closed over this variable that existed up here. And when this eventually ends up getting called over here, it remembers that the factor was 10. That's functional composition. And if you wrote that out with just arrow functions, you would get factor, number times factor. And for those of you who took calculus and what have you in school, that should look an awful lot like f of g of x, because it's exactly what it is. And just like in calculus, you could use it like multiply by 10 f of g of x. Whew. Shit's heavy. Ask me some questions.
So with number, is it doing something similar that it does with factor? Because it's not a parameter. You're not calling it in multiply. So it stores number, or it knows to take that in as an argument as well?
So this is a function. It's a function that takes in a number and returns that number multiplied by a factor. The cool thing, the thing that is new to us, is you can do that in 2 steps here. You can give it the factor first, and then multiply by 10 becomes like a saved version of this that has 10 as the, like, fixed as the factor. And then when map ends up calling it, it remembers what the factor was. But we don't have to use it in the map. It's also just a regular old function. By console log, multiply by 10, 10, I'm going to get back 100.
So then you'd have to reset the multiply by parentheses 10 to something else if you wanted to switch that factor up.
Now I've got both of them.
So is this just another way to create a callback function?
Kind of. It sort of looks like that, right? Callbacks specifically are a response to asynchronous things. So like our fetch requests, or technically an event handler is a handler, not a callback, but similar kind of thing, right? We're using some of those same ideas, but we would call this composition.
Got it.
Ends up looking a lot like callback functions, though. And callback functions are doing the same sort of thing. We can build complex behavior out of simple behavior. We compose it. Another mental model for this. All software is effectively taking inputs and generating outputs. And everything inside this box is the program. And this keeps on going down. We have programs inside of these. So maybe those end up going here, and this one ends up going here and here, and then those combine into here, and that generates these. And then each one of those, all the way down. So with functional programming, what we're trying to do is make all of these little boxes self-contained. State is when these things are all in here, and all these represent variables that can be in all kinds of different combinations. That's state. With functional programming, we're trying to eliminate that so that each one of these is effectively a self-contained program, like this sized. And then we just combine them and combine them and combine them and combine them and combine them until we have all the behaviors we need for the program.
So if I'm understanding this correctly, the
Mhm.
reason to create that is effectively so that you can chain however many functions you need to together to get from input to output. Is that right?
Yes, that's exactly it.
So it's a disadvantage to this approach. Would it be like the more complex your application becomes, the harder it is to kind of trace, the root input or keep track of like all the, I guess, implications of changing one thing because now you've got like a nested web?
So it's actually a solution to that problem, because since these things are all self-contained, who gives a shit what the original whatever is? Like, we're combining these in more complicated Legos and then just sticking the Legos together. The individual Legos, all they need to know is the brick on top of them and the brick under them. Versus if we have a bunch of state that we have to worry about, if each of these are modifying class variables and instance variables, okay, is there some combination of values where when you call this, it breaks? Probably. Are you sure that you've prevented that from happening? I hope so. That's a rat's nest. Here's how you use this in practice. I think that functional programming is especially well suited for data transformations. I gave a talk on this pretty recently that you might enjoy if this is like singing your heart song. Data transformations with Lodash. So in this talk, the goal was to take data that looked like this and then make it look like this. This is like such a bread and butter part of being a programmer. Since it's called munging, you're taking data from one format and then reorganizing it in a different way. Keys becoming values of objects, and these things being split out into other things. Arrays becoming objects, objects becoming arrays. Like, this is such like a day in, day out kind of thing that you do as a programmer. And so I think functional programming is extremely well suited for this. Because to do this with imperative programming, you end up writing loops inside of loops, inside of loops, inside of loops. You get your variables wrong. You get your greater than and less than signs wrong. You add something to the wrong thing. And a lot of times too, it's so hard to tell when you made a mistake. All right, I was supposed to add the duration to the start time, but I actually added it to another duration. Well, they're both going to show up as numbers. How do you know it's the wrong number? Oy. So a functional solution to that ends up looking like Lodash talk. So this is the imperative one. Like I solved it with imperative code. It looks like this: nested for loops, ifs inside of nested for loops, ifs after ifs, all kinds of like mutation and modifying. And I think I even pointed this out in the in this talk. So that's the imperative solution. All of these things are mutations. Mutations are state changes. So the state's changing here. Each one of those is an opportunity for the application to get into an illegal state and break. The functional solution to it looks like this. Damn. A lot cleaner. lot easier to change down the road. In a year, the chance that you're going to be able to figure out what the fuck is happening in those 29 lines. I wrote this. I can't figure it out. That, give me that all day, every day. And these are examples of functional composition. There's a thing called group by, or easier to understand with this one. This takes in an object and emits a property. If you tell it what the property is, then you get a new function where if you call emit user ID and then pass an object, it's going to return a new object that doesn't have this field. Functional composition. Then you can use that in a map and go, all right, I want to take in an array of objects, and whenever I call emit all user IDs and pass in that array of objects, it gets rid of the user ID in all of them. Composition. Ask me some questions.
Do you refactor, or I don't know how you call changing from imperative to the other one, functional? Do you do it yourself?
Yeah.
Manually?
Yeah, so like for this talk, I wrote this one first, and then I wrote tests for it. So this is the test. That's the start, that's the end. I expect that when I call that with that, it works right. So the refactoring is, all right, it worked with that. Now I'm trying to make it functional. So the proof is in the pudding. If it still works after I make the functional transformation, then I did it correctly. Yeah. So I don't think we did super good on our objective for this lesson, but let's recap a little bit. These are the things I wanted you to be able to talk about. I don't think we got so very far into this. First class and higher order functions, you should be increasingly comfortable with this idea. That a function is just some value, just like Boolean, just like string, just like a number. You can also just store that in a variable. You can pass it into something like we're doing here. Couldn't do that in Ruby. Ruby doesn't have functions as methods. Methods are on objects. You can't separate them out from the objects they're on. You totally can in FP and JavaScript. Peer functions. Peer functions are ones that don't have side effects. Side effects are anything that changes something outside of the function. That was this stuff. So every time you've done something like every time I call increment, it's changing something outside of the function. It doesn't own count. So we say that that is a side effect. Versus if I did that as function increment that takes in a number and returns the number, or sorry, a number and an amount, and returns the number plus the amount. The entire thing is self-contained now. It doesn't have side effects. So now I'm doing something like let count equals 0, and then count equals increment count 1. Now increment is pure. Not pure, pure. Recursion, out of scope for today. Recursion is how you do looping in this. So in a purely functional language, no conditionals, no loops, no variables, or no variable mutation. Like almost none of the things that like we started with in programming. So the way that we do looping instead is the thing called recursion. Recursion is a function that calls itself with like an increasingly smaller value. And it checks to see if the value has met some condition called a base case. It solves the exact same problem as looping. Don't worry about lazy evaluation. Type systems, so probably also a little out of scope for today, but type systems are the idea that in addition to splitting out all of these like transformations and stuff, we can also say the specific kinds of types for each one of them. It's like that's a number and that's a number, and ergo the result of calling this is a number, but the type that this returns is a function, and so on. And if we know what those types are, there's a whole bunch of errors that we can catch before we even run the code. Those are type systems. Referential transparency is everywhere that I use an expression, I can swap that out for the result of the expression. So for example, I could do multiply, multiply by 10, 10. I could also do multiply by 10. So that's what the definition of that function is. Well, if that's the definition of it, then I can use it in the exact same way, including like invoking it twice in a row like that. Those are identical. And actually, so is that. Referential transparency means that these three statements are completely equivalent. And then
Well, is that sort of like, I don't care how you got there, the output's all I care about?
Ding, 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 ding. I care what it evaluates to. That it has to do a calculation or doesn't have to do a calculation or gets it from space or a goblin, I don't give a fuck.
For your console log multiply by, and then you have like 10 and 10. Is the first parentheses the factor and the second parentheses the number?
Yes.
Okay.
Exactly.
So outside in.
Yes.
Okay.
So since the definition of multiply by 10 is multiply by invoked with 10, that means that those two expressions are interchangeable.
Cool.
And that's a big idea in functional programming, because since we don't have side effects, the von Neumann like style was, I am assigning the result of this thing into a container. In functional programming, this is a statement of fact, like it is in math. If I say y equals mx plus b, y can't also equal something else that would negate that. If x is 3, x can't be 2 on the next line. That wouldn't make any fucking sense. Functional programming is more like that. And because of that, just like in math, everywhere that I can use 2, I can also use 1 plus 1. Everywhere that I'm using multiply by 10, I can swap that out for this and the other way around. It's the commutative property. So that's why these two things are the same thing. And then lastly, last tenet on here, these data structures. So in object-oriented programming, we were trying to jam state and behavior together. Functional programming, we're trying to rip them apart. We're trying to only describe the behavior, and we're going to try to describe it in an abstract enough way that it'll work with any data that has the right shape. All right, that's your crash course in functional programming. Questions? Does your head hurt yet? So, if this lit a fire in your soul and you want to explore this idea more, Functional JavaScript by Michael Fogus is a great next step. I think it is the single best, here it is. It's the single best, like, easy intro into functional programming, because everything else, man, like, goes real heavy on the math. It's almost like they're like, hey, so you know how you're a math expert? Here's how you would apply that to programming, rather than the other way around, where it's like, hey, are you comfortable with JavaScript? Neat. Like, here's how you would understand some of the math underlying this. It's still a heavy read, like not like in size, it's 262 pages, but it's still a lot. Functional programming is hard, but if you can dedicate some time to this over your career, like, it'll carve you out of wood. You'll write such better code with some understanding of this, and especially for this kind of stuff, which, as I said, bread and butter kind of programming work that we do. Going once. Twice.
Well, I have a question, but I'm not exactly sure how to phrase it. I'm trying to figure out. So I'm picturing that the functional program is probably used in like big servers and stuff, and trying to transform like emails and do all this kind of stuff. What's the relationship? So how would you be using functional programming to interact with OOP?
So, like, you might have an OOP method on an object that does a data transformation. You could write that functionally. That's how you mix and match them. And that's actually pretty common. I do that a lot. Use OOP for very high level pieces of the application, because I think functional is actually pretty bad at that, especially for web apps. And then when we get down to anything that's transforming data, switch into functional mode. And JavaScript's awesome because it does both of those pretty well. You get a lot of flexibility with these multi-paradigm languages.
So I imagine like, if you are able to write all of these nested functions, that there's probably my comment was facetious, but like I imagine there is like protocol for not blowing up your shit.
Yeah.
So I imagine that's like a whole other part of this, is like learning how to not do that.
Oh, absolutely. So Like if you're using this in scientific computing or on rocket ships or things like that, you want it to be like a mathematical proof. You want to be able to exhaustively say any legal input for this will produce a legal value. And with functional programming, you can do that, especially in a purely functional language. You can write these as math proofs and then execute them. That's powerful. All right, ladies and gentlemen, after a year, I am about to go walk out to my kitchen and sign my refi paperwork. All right, I'm going to go close. See you guys. Hopefully,
Thank you, Kyle.
Cheers.